All right, so today I will present the work I did in the past month on UK case study. I will present method for energy footprints and initial results from linking it to well-being, and and what can I see from those links. So my aims are to see how well-being is achieved depending on different satisfaction of needs. So what kind of satisfiers households use to achieve their well-being. So I'm wondering if there is a difference between type of transport that people use, maybe also the type of activities. So broadly, provisioning systems today, and how do they influence achieving well-being and energy footprints? And can we see any lock-ins? Can we see any pressure points that pull the people to be locked, or maybe not, in specific lifestyles and specific types of energy use, and what kind of results it has on their overall well-being. So currently I work in a frame of kind of looking into different types of households. So here you can see that I grouped, so that's kind of like just the conceptualization, how I grouped households based on if they have high well-being and low energy footprint, that would be quadrant 1. If they have high energy footprint and high well-being, or maybe low energy footprint and low well-being, and the quadrant 4, high energy and low well-being. So I will be exploring these different types of, or different groups of households, and see what are kind of interconnections or differences between different quadrants, and can we see kind of way out from high lock-ins, high energy lock-ins, and how also what is enabling households to also achieve higher well-being with lower energy footprint. So, okay, this is for aims. And to do the study, I need, of course, data. And I base my energy footprints or calculations on, and also well-being characteristics on Understanding Society survey, which is UK household longitudinal study. It started in 1991 and it's still ongoing. It's brilliant it's a brilliant study that has a lot of different modules, has questions related to health and well-being, different socioeconomic characteristics, anything from income to location, to type of employment, to family life as well. Environmental attitudes sometimes pop in the different waves of the study. There is also module about transportation, financial behavior, like how much people save, and much more. But at the same time, there is not much on expenditure. So we don't have expenditure module, and this is a problem, because energy footprints usually are calculated based on expenditures. So 4 methods how I can calculate those energy footprints if I don't have expenditures. So I statistically match 2 household surveys. So it will be it might be a little bit confusing, so just bear with me. So first of all, I used living cost and food survey. And in that survey, we have expenditures. Households are asked to have 2 weeks diary where they put all the expenditures that they, all the spending that they did have in the last 2 weeks. And they include everything from how many bread of rolls they bought to if they buy a car, or if they spend anything on restaurants or going out. So this, together with data from International Energy Agency, which is which includes final energy use. So with the energy use data, this can be used in the UK MREO model, which basically takes expenditures, energy data, and international trade between different economies and calculates how and gives the conversion factors that can be used to calculate energy footprints. So conversion factors that are a result of these of the multi-regional input-output method, which is consumption-based. In this case, results in conversion factors that are expressed in megajoule per pound, which is, for example, you would have how much energy per pound spent on bread household used. So that's in the living cost and food survey. And back to the understanding society survey. In that survey, we do have some expenditures. So we have expenditures on electricity, gas, and other fuels, house fuels, on restaurant and groceries. And also we have some physical quantities, like how many miles a person have driven in the last year, or how many flights the person took. So this information can be used together with conversion factors from living cost and food survey. And this is how I can obtain energy footprints. But we don't have all categories. So we don't have footprints related to clothing, or we don't have footprints related to communication, education, leisure. So to be able to do that, I had to statistically match those two household surveys. So what statistical matching means? So if you have two surveys that are from around the same time and share number of different socioeconomic variables like income, household size, working hours, type of household, education. So if you find this type of characteristics in both surveys, and if these characteristics have a similar distribution in both surveys, so income is similarly distributed among the sample in the living cost and food survey as it is in understanding society, like if you have a match, you can use one survey, in this case living cost, to predict values for another survey. So you can use living cost and food survey as a vehicle to kind of predict what would be energy footprint of households in understanding society, because they share so many similarities. And that's what I did for several categories in several energy footprint categories. So for housing, water, refuse, for recreation, package holidays, for communication, education, and some parts of the public transport, I used regression analysis to predict values for understanding society households based on living costs and food survey. All right, so that was I think the most convoluted part. But however, some of the footprints, some of the models, regression models, were too weak to be able to make a meaningful prediction. And for these categories, which are listed on the slide, I used average energy per income decile. Because income is similarly distributed in both surveys, I just use what is the average footprint for example, clothing in the first income decile, and applied that energy use to the income, to the households in understanding society with the level of income corresponding to first decile. Yes, and just a few words on the house fuels. So I did say for the simplicity that I use conversion factors. However, for electricity and gas, I had additional information. So the prices of energy in UK, they differ by region. So between some regions, it's a slight difference, but between some others, there is a little bit higher difference. And because the footprints are based on expenditures, I did recalculated the use of energy. So using the difference between regions and payment method, I was able to calculate kind of backwards how much they spent to how much kilowatt hours household used. And with this, I could just convert to a megajoule. And some households had missing expenditures on electricity and gas, and I used statistical imputation to impute these values for the expenditures for households that had missed spendings. And for the transport, I did mention that I have information about mileage, but this was also in addition to having information about engine size and fuel type that household used on the private transportation, which is great because that gives me a better, more accurate energy footprints. I was able to calculate it more accurately. What are the footprints corresponding to private transportation? So just to give a final result, so this is a comparison between between living cost food survey and understanding society, and by income decile. So on the horizontal axis, you can see from 1st to the 10th income decile, and the footprints are represented for different categories, and they do look alike. So that gives me a confidence that it's not a black magic that I just did, but actually it's the method used and the information I used yield a quite good statistical matching and calculation of energy footprints. And this is by share. So we can see that actually the footprints are quite similarly distributed, at least by income deciles. Yes. So quickly to initial results. I showed before the 4 quadrants of different types of households, and before I kind of go to what I found in each quadrant, I want to shortly say what indicator I used for well-being. There's a lot of information linked to physical or mental health in understanding society, and I combined 2 indices, mental health and physical health index. And as much some of the questions that are used for building each of the indices might be you might kind of see, okay, maybe it's not the best question to use, or maybe it's not the best variable. I think it gives a quite good comprehensive picture for well-being indicator. And for the energy, I use different levels, which I will say about now. So for the low energy footprint, I used a global average in 2018, which was around 55 gigajoule per capita. And for the higher end, I used around 158 gigajoule of energy per capita. So my initial results have 4 groups, which I called Goldenberg households, which consist mostly of young, urban, and healthy people. Then wealthy and healthy, rich, old, and educated, who are having a very high energy footprint while having high well-being. Stuck at home, people that are poor but and seemingly stuck at home and cold and are sick. and money can buy, sick, but rich and educated. So just quickly to go through some of the characteristics of these households. So in the Golderberg households, I find that majority of these households are urban, have their work close by home, have on average one car, earn £500 less than the overall average, do not have so much autonomy over choice of hours of work, and on average they don't work any different from the overall average. And we see the result in, we see the kind of impact of economy of scale with the household size. So on average, it is 4 people per household. And I repeated the working close by home. And they do not have a big footprints when it comes to flying or private transportation. So these two kind of regions were the most, these two categories enable them to save a lot of energy. Then wealthy and healthy, they mostly are rural. So there is big share of households that live rurally, and the household size usually is 2. They are mostly the most educated out of all the 4 quadrants, and they're quite old. 2/3 of the sample is 50+ years old. They can choose more, they can be more flexible to decide when it comes to autonomy at work, and but they don't overwork themselves too much, and they want to retire soon. And I think that's the group that is able to retire at age of 60. But they will not die anytime soon because they are very healthy. They report the having excellent health, and their subjective well-being is also very high. They think they do quite a bit for environment, but obviously their footprint is very, very high. And they manage to save a lot of money that potentially can be spent in the future on trips to can be spent on flying, for example, or more transportation on the retirement. And stuck at home, this is very similar to what Milena found in her study. Milena Books, what she found in her study, that I think is also actually called her study Stuck at Home, which the title I took for this group. They work much less than any other groups, and I think because they're sick. They only 4% claim to have excellent health. Majority of them also claim to have some long-lasting illness or disability. They report to be more lonely, but they do a lot for environment, or at least they claim, which also shows in their energy footprints. And also twice as many report to not have adequate heating at home, compared to 5%. So compared to the average, overall average. So there is a lot. I think when it comes to energy poverty, this is a group that is very energy poor. And the 4th quadrant, they also mostly rural. They're also quite educated. And even though they are kind of in between, they earn 1,200 less pounds than the healthy and wealthy, but at the same time 1,200 pounds more than the overall average. But they don't save much. Usually they just save maximum 500 pounds per month. And their lifestyle is very similar to the wealthy and healthy, which means they fly and drive a lot. So this is kind of my first initial results, and I will be digging into it more in coming days. So there is more to look forward to. And this is where I want to finish, I think, for now. Yeah. Thank you.
I'm now going to talk about something much more humble, which is emissions trends. So no well-being, but purely thinking about emissions trends by sector and by country. And the background to this research is really all about IPCC and the 6th assessment report. And so I ended up essentially responsible for the emissions analysis of the 6th assessment report. I'm the chapter scientist in chapter 2, which is emissions trends and drivers, but this data is basically used in all of the sector chapters to track trends sector by sector. Also to look at emissions trends in regions, and all of this filters into like the main summary documents and all that kind of stuff. So it's been a huge project, and it's like the #1 thing that's responsible for me being a bad collaborator these days. So sorry to a few people in this room, especially Julia, Yefin, and Elka. But this has really been like an overwhelming task. But I'm coming to the end of it, and there are 2 products already coming out before the report. And one of them was published this morning, and that is a review of trends and drivers of GHG emissions by sector. And the second is a paper which is more focusing on countries, so what progress have countries made in reducing emissions. And those are the 2 things I'm gonna quickly talk about. So for the first, right, so where does emissions data actually come from? This is interesting. This I did not know before I started, right? So all of those countries in blue, they are required by the UNFCCC to submit a spreadsheet that follows IPCC protocols in counting up emissions by sector, by gas, etc. And then they hand that over, and those are held in a nice repository on the UNFCCC website. All of the other countries, the countries not in blue, are not required to submit that kind of information every year. So the end effect is that we have major countries responsible for large portions of global emissions that have completely out-of-date inventory data. And that includes China, which hasn't submitted anything in 5 years, India, like over a decade, Brazil, over a decade. And so global emissions are covering all countries is really more guesswork. And that guesswork comes from activity data, technology mixes, emissions factors, and sort of a big combination of all sorts of like really detailed data that comes from national accounts, but also estimations. And the main people involved in doing that are the IEA, EDGAR team at the Joint Research Center in Europe, CDAC in the United States, and yes, BP. So here in this paper and in the IPCC, we're using EDGAR. And EDGAR has good coverage of greenhouse gas emissions for all countries. And we're supplementing that with land use CO2 emissions, which comes from 3 bookkeeping models. So I'll describe what that means as well. IEA, from the IEA, we get indirect CO2 emissions, and I shall also explain that now. So here is one of the main figures that's going into the SPM, and that is the breakup of emissions by sector and by subsector. So the main story for me here is that there are no single big apples. There are no big sources of emissions, but there are lots of medium sources. Of course, on the one hand, electricity and heat. So this sector is all of your gas power plants, your coal power plants, and the direct emissions coming from those. That does account for 24% of emissions, but you can reallocate that. So using the IEA indirect emissions data set, you can reallocate that down to sectors and have more of a demand perspective. So that means here we count the emissions used in buildings coming from electricity and heat sector. And so from that perspective, industry is big, agriculture is big here in blue, transport stays about the same at 14%, and buildings goes up to 17%. And the main chunks there are like residential emissions. So here's another perspective. Here's the same list of subsectors, and here you can see the reallocation of electricity and heat, and then the ranking of how big these are globally. So residential buildings is very large, road transport is very large, metals, chemicals, non-residential buildings. Land use CO2. Land use CO2 is the emissions that occur when you change from one type of land use to another. So you cut down a forest and you put cows, during some grass, or you cut down some forest and you plant palm oil. Those are the main things that happen actually to cause emissions in this sector. That releases a lot of CO2 emissions. And then you can see that these are differently colored. So you have green, the CO2 emissions. Gray is also CO2 emissions, but indirect, coming from the electricity and heat sector. And then we have other components that comprise like methane emissions in agricultural sectors, also fugitive emissions from methane, and F-gases. So these different sources have different uncertainties, different levels of verification, different levels of scrutiny. Land use CO2 emissions, this very, very large chunk, is extremely uncertain. So there's nobody going around sticking measurement things into the ground and understanding like how much carbon is there and how much carbon is in biomass. This all comes from bookkeeping models that basically have a fairly good representation of what types of land use exist around the world and how it's changing over time. And here we use 3 bookkeeping models, which is the standard in the first working group of IPCC, and they vary enormously. So there's a huge gap between 2 of them, and then one sort of in the middle, and we take the mean. And the estimated uncertainty here is like 60%. So this could be like 3 gigatons higher or 3 gigatons lower, and depending on the country and so forth, can really picking out the trend in this sector is very problematic. Fugitive methane emissions are another tricky sector. So this is all the leaks of gas coming from your oil and gas infrastructure. So gas leaking from the wells, from the pipelines, from the appliances. There's been recent studies that look at top-down measurements of atmospheric methane, and they find that, well, we're really undercounting this sector because you can trace the exact type of methane in the atmosphere to the underlying fossil fuel source. The uncertainty here is enormous. It could be between 65 and 90%, even in countries like the United States. So the EPA is constantly revising this sector based on better data. F-gases is another uncertain source. So those are all the gases that are left over after the Montreal Protocol came in after the 1990s. So we're not allowed F-gases, fluorinated gases that chew up ozone anymore, but we're still allowed to release fluorinated gases that are like 10,000, 15,000 times more powerful than CO2. So they are low in volume, but they have a very high effect, and they come from few sources, and they're not really well tracked either. So the uncertainties by sector, so they're quite low for transport and buildings. So we know that this is mostly fossil CO2, petrol. It's quite uniform type of fuel. We know the emissions factors, and that's fairly okay. Uncertainties are medium to high for industry because it has large chunks of F-gases. It has quite a lot of methane from waste emissions that are not well counted. And it's very, very high for agriculture, forestry and other land use, and also fugitive emissions, like I mentioned. So I'm just going to whiz through a few highlights. So we got one of these. This is basically the emissions plot in our chapter, and we've got one in every single sector. So industry, energy, this is a total one. And here you can see the distribution of sectors. You can see the regions and how they've changed over time since the 1990s. The main insight there is that East Asia has been absolutely taking off in the last decades. That's China. And the other largest emitters are North America and Europe. And those are mainly from energy and industry emissions. Different perspective is from these developing regions like Africa, Latin America, Southeast Asia. There it's agriculture that's really the major source. So a few highlights like energy system emissions. So this is electricity and heat. That's, like I said, all of the coal power plants, gas power plants. This took off in the last few decades because of China. So huge, huge growth between 2000 and 2010, about 3% per year. And that's when they were building all their coal power plants. This started to slow down around about 5 years ago. And then people started to think, maybe we've reached a peak in CO2 emissions, but then it went up again. It turned out that China was just adding fewer coal capacity additions, and economic growth slowed down a little bit. By contrast, we've got decreasing energy system emissions in Europe and North America, and this is mainly related to switching of fuels, so coal to gas, particularly centered around the fracking boom in the United States, and like this slow growth of or steady growth of renewable deployments in Europe. Industry, like the main thing going on here is that surprised me is just the huge concentration of industry emissions in China. Like if you add up all these other regions, you could probably fit most of them in here. So this is just really where the whole story around industry emissions are happening worldwide. Transport, you can go look at Julio's thread on Twitter, which he wrote this morning. It's a steady growth globally, and it's the only sector that's growing in every single region around the world. And it's mostly cars, it's mostly road. Agriculture, here's an interesting one. So this is land use CO2 emissions. Again, that accounts for the largest chunk. And it's all about these three regions, Africa, Latin America, and Southeast Asia, where pristine and semi-pristine forests are being cleared and converted into other types of land use. By contrast, in the Northern Hemisphere, we chopped down a forest centuries ago. So we no longer have these emissions. That legacy is now gone. But these land use sinks are starting to regrow at a sort of slow to steady rate in these regions as well, which accounts for those negative values. Buildings is very tightly linked to the energy sector. So here in the colored bars are the direct building emissions. That's like if you burn coal in a coal boiler or a gas boiler or something like that. Biomass used in homes. That's been steady globally and not really reducing much in different regions. And all of the trend really comes from the upstream energy sector emissions if you reallocate them here in gray. So it's tied to the electricity and heat sector. So there's a big paper, there's a lot going on. We try to descriptively link these overall changes by sector and by region to underlying activities and trends. And basically we structure them by chi factors. So it's descriptive in the sense that we build on the literature and we use experts. And the good news is we have some really great experts in this paper. So Julio is covering transport sector. We have Dominic Wiedenhofer for industry, Yamina Saheb for buildings, Julia Pongratz for agriculture, Robbie Andrew for the energy sector. So some really great people. And that's like, I'm making the appeal to expertise here because the literature is just all over the place, and it's very, very difficult to try and give an overall sense of what's driving these, but we try to break it down into basically features of demand. So in the industry sector, it's all about materials and material growth and use. In transport, it's all about travel demand. In buildings, floor area, and in agriculture, what's happening on land. We also looked at shifts in fuel type, so coal to gas, petrol to electric, fossil to renewable, and efficiency of different modes of provisioning, like vehicle type, buildings, energy efficiency, and so forth. And the main insight overall across these sectors is that efficiency is improving in every sector. That's nice and that's expected. Shifts in fuel type are very, very specific to the sector and very specific to the country. So in a few countries, you have some small shifts from coal to gas, fossil to renewable, etc. But otherwise, globally, it's continuing continuing dependence on fossil fuels. And then, but by far the biggest driver is the demand. These demand factors, right, that are not changing. So that's that paper, and that gives like an overall sort of perspective. Now, I would quickly do a few more slides that's talking about progress in national greenhouse gas emissions reductions. The reason I want to talk about this is that like it's just a newly common theme. Everyone's talking about progress in emissions. Like here's the Prime Minister of Australia saying a few weeks ago we reduced our emissions by 19% on 2005 levels. This is 36% when you exclude exports and this kind of nonsense. Ivanka Trump as well. But if we go back to that first paper, globally, what's really improving, what's really changing at a significant pace in order to really deal with this problem and bring down emissions to where they need to be. And so really see this as a parallel story to what's going on with climate denial. You can represent emissions data in a non-neutral way, that you can cherry pick it, you can twist it, you can take it out of context, and you can miss the bigger picture. So what I would like to do is try to develop some sort of critical questions, rules of thumb to guide inoculation strategies. So what does emissions reduction progress actually look like, and how should we talk about it? And how can we protect against these kind of disingenuous discourses? So what I've tried to do is build up a picture of countries that are, from my perspective, making progress. And so these are countries that have sustained continuous reductions in CO2 emissions over a period of at least 10 years. They've reduced GHG emissions over the same period, and they're not recently listed as fragile states. So they're not experiencing measures of economic trauma in recent years. And so there you see, in green, you have CO2 emissions, in blue, GHG emissions, in orange, consumption-based CO2 emissions. And all of these are on a sort of downward trend. You can see that some trends are shorter, some are longer. And that relates to basically three types of emission reduction pathway. So recently peaking countries, where there was a continuous growth up until about 2005, and then they peaked around about then and have been reducing emissions ever since. That includes the United States, Spain, Portugal, Finland, Italy, and a few others. Then there have been your old industrial economies like the UK, France, Germany, Sweden, that have been reducing emissions like year after year for several decades now. We call them long-term decline. And then there's a former Eastern Bloc, so countries that were in the sort of sphere of influence of the former Soviet Union, which had a collapse in the 1990s. That led to a very drastic reduction in economic activity and emissions. But in these specific countries, so not the whole former Soviet Union, but in these specific countries, some sort of structural change led to continuing reductions thereafter. And you can see that these were actually very, very significant drops, right? 65% drop in CO2 emissions since peak years. And what's interesting here is the importance of contrasting CO2 versus total greenhouse gas emissions. And you don't often see this. So let's take the example of the United States, right? The US has been reducing emissions by 1.2% per year for about 10 to 15 years. That sounds good and that's nice. And the story there is they have had this shale gas boom. They've been shifting away from coal relatively quickly. So building up all of the gas infrastructure and gas power plants. Gas has lower CO2 emissions than coal, but it has higher methane emissions. And so if you take into account those methane emissions, then all of those changes are basically wiped out. So remember what we were talking about before, fugitive emissions leaks, like methane leaking from the oil and gas infrastructure. Once you take that into account, changes drop to basically zero. A similar but different story occurs in like large agricultural economies like Ireland and Denmark that made progress on the energy system side, but didn't make progress on the agriculture side. And there it's like really important to look at the sector detail. Yeah, so here, these different groups of countries, all of them made progress in terms of reducing electricity and heat emissions. None of them made progress in reducing transport emissions. And many of them had a sort of rebound in this fugitive emissions category. So that methane bouncing back. And a lot of them were sort of sticky in quite a few other agriculture industry sectors. Interesting thing to look at is which countries failed. So if we take all the Annex 1 countries, which ones didn't actually manage to reduce emissions? Here we have like Russia, Australia, Canada, Norway, etc. And here what I've done is added in the land use CO2 emissions. So in this paper, I didn't actually have the land use emissions because it's so unstable, it's so uncertain. But what Australia likes to do is say, yeah, once we include land use CO2, we've been reducing emissions. Now, that is kind of true if you include the FAO data for land use CO2. You can see it gets pushed up and flattened a little bit. That's the pink line, including land use with GHG. But is it a total emissions reduction? Is it really making progress? There again, in Canada, you can see the massive uncertainty around this sector, a huge jump in like 2000, and then it's been coming down ever since. So a policymaker could say, yeah, we've been reducing emissions in our country for about 10 years now, if we include this kind of sector. So keeping an eye on those differences between the sectors, the emissions, the GHGs, the CO2, and the land use is really, really important. So I would have a few rules of thumb to challenge these kind of success narratives. So first is, how recent were emissions reductions? The main thing is uncertainties are just too high for individual years. So success looks consistent, it looks long-term. And you see a lot of dodgy stuff happening with COVID right now, and people saying, yeah, we've had a massive drop in emissions this year. It's got to be long-term, it's got to be longer than 5 to 10 years. Are reductions fast enough? Rule of thumb is usually no. None of these are really within the bounds of 2 degree, 1.5 degree scenarios. In which sectors were they achieved is a key question to ask. Fuel switching is just not a long-term solution, both in terms of the total GHG emissions and in terms of the lifetimes of that infrastructure. And also countries can really hide behind land use change removals. So if you think something's going on there, then it's probably dodgy. And what is a plan for future reductions? So concrete policies need to address all sectors. They need to deal with transport, they need to deal with industry, etc. So that's yeah, a quick whiz through some IPCC data stuff. Thank you.